Good. So nice to see people online and those in the room as well. So yeah,
so getting here.
You can do go on, come in. So I'm Jonathan Hargreaves, as most of you know. This is Lewis MacDonald, who did the Eng in acoustical and audio engineering here. Is that the right topic at the time? Or was it a different name? Audio acoustics. Audio acoustics it was called at the time. Same thing, different brand name. And then he so he kind of did that, and then he did a project with me on horn optimization, which kind of was supposed to be a bit of simulation and measurement, wasn't it? But COVID kind of hit, so it ended up being a simulation project. We managed to get a reproduced sound paper off that, which was really nice. Went and talked about that at the IOA Reproduced Sound Conference. And then off the back of that, we're talking to Mark Dodd and Jack Ockley-Brown at KEF and Celestion, and they were quite interested in his work, so they proposed a project, and Lewis stayed on and did a Masters by Research, again, kind of under my supervision, but with some industrial steering from them, working on optimization methodology related to a new kind of horn design that Mark Dodd over there had got patent pending at the time. And so that kind of went through, and then at the end of that they took Lewis on as an R&D engineer. So he's currently still working there, still working on the same thing. I think basically going to take us through this process, which is metric-based waveguide optimization. And yeah, and if anybody of you want to chat to Lewis afterwards, so he says Lewis is working Celestion, but somehow managed to swing it to be based in Devon, so he can still surf. So I think he's winning at life. So there you go. So thank you very much.
Yeah, thanks for the introduction, John. So my name is Lewis MacDonald, and today I'm going to talk about metric-based waveguide optimization, or as we've been calling it. Hang on, let's click. This slide.
Just click on that window, that'll probably work.
There we go. Yeah, as we've been calling it, the Lensguide technology. So a bit about me. I feel like John just covered most of this, but I'll go through it again. So yeah, I did the audio acoustics bench or bachelor's engineering at Salford. I did an internship at Timpany UK DC in Wales, doing like designing loudspeaker drivers, and then I did my final year dissertation on mid-range horns and phase plugs, and as John just mentioned, did an IOA paper off the back of that. John then sent this dissertation to some of the engineers at KEF and Celestion, who suggested I did a research project, so big shout out to John, because I would have been stood here if he hadn't done that. And then I did audio acoustics masters in research, which if anyone doesn't know is just like one big research project. You don't have any modules, it's just like a huge dissertation over 2 years. This was supervised by John, and I had some support from the engineers at KEF and Celestion. And then during that I started doing like part-time work for them, and then after I'd finished the Masters in Research I started working for them full-time, which is what I'm still doing at the moment. So yeah, my day-to-day job involves loads of MATLAB and FEA, if anyone was interested. So KEF and Celestion are both companies which are part of GP Acoustics. KEF was founded in 1962, and they do hi-fi loudspeakers, architectural installation loudspeakers, and wireless and active streaming loudspeakers. Celestion was founded in 1924. We recently had our 100-year anniversary party, and they do loudspeakers for guitar, drivers for PA, and compression drivers for PA. So it's Celestion which this research is more directed towards, because it's sort of a pro audio project, and it's Celestion that I work for. So some acknowledgements. This seminar summarises the following publications. The first one is by Mark Dodd and Jack Ockley-Brown, pictured there. Mark is head of group research at GP Acoustics, and Jack is the VP of technology at KEF. And this paper is wave shaping using novel single parameter waveguides. The next one is the one that came out of my Masters in Research, and this is by myself, Jack, and John, and this is metric-based development of acoustic lenses and waveguides. And then the final one is iterative metric-based waveguide optimisation, and this is by all four of us. So a summary of what I'll talk about. I'll start off with some background horn acoustics and why there's a need for new waveguide technologies. Then discuss 1P or single parameter waves, a new approach called Lensguide, some examples of some waveguide metrics, how these metrics can be used in an iterative optimization process, and then an optimized line array waveguide, and finally some other examples of how this tech can be used. So some basic background stuff. Horns, they're widely used in professional audio systems. Here's some pictures of horns with really nice background shading and the lights. They are used mostly for two reasons: to improve the efficiency of the system, so they match the impedance of the driver to the air, and then they are also used for the directivity control, which is especially the case for high frequency devices in Pro PA. Geometric design of horns is really important as it affects both the directivity and the frequency response of the horn driver system. So for this presentation, I'm going to use this definition of a waveguide, which is a type of horn design primarily to guide and shape sound waves. The main purpose of a waveguide is directivity control rather than loading. So compression drivers are drivers which are designed to be connected to horns. The diaphragm area is larger than the throat area, so you get this compression, which is why they're called compression drivers. This leads to really high efficiency because there's a high resistive load on the diaphragm. The directivity is determined by the horn and not the driver. And horn loading is mandatory because without it, the diaphragm excursion is uncontrolled. So I'm going to look at two different types of horns to compare. So the first is exponential horns. Exponential horns have a constant flare rate throughout the horn, so this means that the expansion in area is continuous as you move down the horn. They have a distinct cut-on frequency. This plot here shows the throat impedance for an exponential horn. The dashed line is the imaginary part, and the solid line is the real resistive part. So above a certain frequency, I think in this example, maybe like 600 Hertz, there's quite a smooth resistive load, which means you'll get high efficiency from the combined driver and horn system. Yeah, they have excellent loading above a cut-on frequency. However, exponential horns have a narrowing in directivity at high frequencies. So as you move off axis, you find that the high frequency energy massively decreases. And this means if you're trying to cover a large audience, it's not a very good horn to use. Next, diffraction horns. Both line arrays and constant directivity horns use a diffraction slot. So here's two examples of this. The bottom is like a line array box, and above that are some of the old school JBL constant directivity horns. And they both have this diffraction slot sort of halfway down the horn. And diffraction slots rely on a sudden change in area expansion after a narrow slot, and this causes the sound waves to diffract, and then you get wide directivity. But this sudden change in area expansion introduces some problems, and I'll show you what they are in a few slides' time. So another thing that I'll cover in this seminar is line array wave shapers. So these are devices which try and convert a circular plane wave from a compression driver into a rectangular plane wave at the exit of the wave shaper. And the idea is you put lots of these on top of each other to create a long line source. So you have a line source even at high frequencies. There are loads and loads of contrasting designs seen in commercial products, and the pressure isn't always constant across that exit surface. So yeah, comparing, I'll just do some really simple FEA simulations of an exponential versus a diffraction horn. So there's the exponential, and here's the diffraction horn. The exponential horn has this like gradual narrowing in frequency, in directivity, sorry, as you go up in frequency, as opposed to the diffraction horn, where now you've got wider directivity up to a higher frequency. And this is why diffraction horns are used a lot in PA, because you can cover more of an audience with high frequencies. This slide compares the same two horns, but now the throat impedance. So throat impedance is controlled by how the area expands through the horn. This is the area expansion of those two horns. The exponential's got this nice smooth expansion area, as opposed to the diffraction horn, which has this sudden change in area. And this causes ripples in the throat impedance, because some of the propagating sound waves actually reflect back up the horn where there's that sudden change in area. This here is the throat impedance of these two horns. The exponential horn's got this nice sort of cut-on frequency and then quite a smooth resistive load above that, as opposed to the diffraction horn, where there's these massive ripples in the throat impedance. And these are then founded in the radiated sound pressure level. So this is just a lump parameter model of a compression driver connected to these two horns. And yeah, the ripples in the throat impedance are then found in the radiated sound pressure level. So you have these massive ripples in the response, which is not very good. So a lot of the time when people are designing horns, they're kind of trading off having good throat impedance or wide directivity over a large bandwidth. And it raises the question, is it possible to have both wide directivity and good throat impedance over a large bandwidth at the same time? Now I'll look at single parameter waves, or 1P waves. In a 1P acoustic field, the pressure depends only on a single spatial coordinate, and that is the distance that the wave has travelled. So this means there's equal pressure magnitude across each entire wavefront. And if you were stood in a 1P acoustic field, as you moved around, not towards the source, but if you moved left and right, then the directivity would be exactly the same at every single frequency. So it's a really nice acoustic scenario. The wave propagation is coherent and free of acoustic resonance and diffraction. So through some rigorous mathematics, a guy called Pathlength defined the necessary conditions for 1P wave propagation. And he showed there's only 3 shapes which support exact 1P wave propagation. And these are planar, cylindrical, or spherical waves, which can be seen in each of these pictures. So you can imagine the wavefront sort of moving through each of the colours. And the thin black lines represent the edges of the domain. So Pathlength's criteria for 1P waves, he outlined 2 necessary conditions for 1P waves to propagate along a coordinate, u, and they look like this. I'm not going to go too much into the maths right now, but if anyone's interested, you can check out his paper. But the geometric interpretation of these conditions is that the distances between the surfaces of constant u must be the same over the entire surface, and all the surfaces of constant u have a uniform mean curvature. So an example of a 1P waveguide is like a wedge with straight sides that are infinitely long. If you were to excite the throat with cylindrical waves, then you'll end up with cylindrical waves propagating outwards at every frequency and with the same amplitude across each entire wavefront. So that would be great directivity. However, in this waveguide, there's insufficient low frequency radiation for it to be useful for practical applications. So this plot here shows this throat impedance for this horn, and yeah, there wouldn't be much sensitivity at lower frequencies. So now introducing this Lensguide technology. Mark Dodd and Jack Oakley-Brown described a new class of wave shaping waveguide, and these thin waveguides use patented corrugations and thickness variations to control the acoustical waves propagating through the device. So this picture here is lifted from the patent, and you can see that there are these corrugations down the edges, and they're used to change the relative path length and keep the distances between the wavefronts the same. These waveguides are essentially better at supporting 1P wave propagation. So an example of this, this is an exponential horn. Again, there's this nice cut-on frequency. However, when you look at the directivity, or this is just the SPO at points A, B, and C, there's loads of high frequency energy at point A, and then as you move off axis, the high frequency energy massively decreases. Now, using this Lensguide approach, where the domain's been given a thickness and there's these corrugations added to the sides, the throat impedance is still pretty good, but now at point A, B, and C, the pressure is really equal, which is quite amazing. It's pretty remarkable results with a really simple approach. So these first ones, these first Lensguide geometries were hand designed or hand generated using 3D CAD. It's really time consuming and intricate, trying to work out exactly where the corrugations should be and how high they should be. And it became quickly clear that new tools would be needed to automate part of the process. This stage of development took considerable time. Loads and loads of different ideas were investigated, but eventually a suitable approach was found with 2 stages. So the first is a method for automatically generating a coordinate system moving through a geometry, and this was done using Laplace's equation. And the next are some metrics that directly indicate the geometric deviation from the condition for 1p waves. So this is Laplace's equation. This is a picture of Laplace. And it's commonly known as the heat equation, so it can be used to model how heat is distributed inside of a domain. It's also a special case of the Helmholtz wave equation, where the wave number k is set to 0, so you can think of it as like a frequency-independent version of the wave equation. So Jack Oakley-Brown proposed an extension to Pathlength's work through applying it to solutions of Laplace's equation. And he proposed 2 waveguide metrics which quantify the deviation of a solution to the deviation of a solution of Laplace's equation from Pathlength's conditions for 1p waves. To calculate these metrics, first the solution to Laplace's equation is calculated over a domain. In this example, I've got like a thickened sine curve shape. The entrance is here, exit is here, and the boundary conditions are just a value of 0 at the entrance and 1 at the end. So if you thought of this as the heat equation, it essentially just models how the temperature changes throughout the geometry. The next step is to trace some streamlines which follow the gradient of U, so from hot to cold. They start here and they move through the geometry all the way to the end. And then both the solution to Laplace's equation and the streamlines are used in the calculation of the waveguide metrics. So today I'll just sort of go through what the waveguide metrics look like, but if anyone's more interested in the sort of like maths and finer details of the calculation, then they can check out the paper. But the first metric is called the stretch metric, and this is related to the relative path length moving through a geometry. So this is that same thickened sine curve shape, and this here shows the stretch metric, which has been normalized to the longest path length at each point. The maximum value of 1 is found on the outside edge of each curve section, as this is where the longest path length is. And the stretch is then less than 1 on the inside edge of each bend, as the path length is shorter in this region, the relative path length. So one way you could think of this is like it's a running track, then the person on the inside edge of the bend is going to end up further in front. And this is useful because path length can then be added to the geometry in regions where the stretch is less than 1. Perhaps something like that with some corrugations. The next metric is the felt area metric, and this is the relative change in cross-sectional area moving through a geometry. So this here shows the felt area metric on a channel joining a wedge, and the felt area metric is unity for the first part of the geometry because the cross-sectional area doesn't change, and then it goes up to around 3.5 at the end of the geometry, and this just indicates that the cross-sectional area is now 3.5 times as large as it was at the beginning. This can be used to adjust a waveguide's thickness so that you can achieve the target area expansion moving through the geometry and then get the desired throat impedance. This plot here shows the felt area metric on that same thickened sine curve shape. Now, interestingly, the change in curvature of the channel causes a propagating single parameter wave to feel a change in area, which is why it's called the felt area metric. So it indicates an increase in area on the outside edge of the bend, and then a decrease in area on the inside edge of the bend. And this is interesting because the domain has a constant width, so the physical area isn't actually changing. So these metrics can be used to automatically correct a waveguide through adding these corrugations. So the corrugations are added to equalise the relative path length through the geometry. The corrugation amplitude is driven directly by the stretch metric. So here's that same mesh, but now it's had these corrugations added to equalise the relative path length. And the 2D mesh is warped, which forms a shell mesh, which uses 2D elements in a 3D space. So the corrugated shell mesh was then reanalysed with the same metrics. So the top plot here is the stretch on the original 2D mesh, and then the bottom one is the stretch on this mesh, which has had these corrugations added to it. And there's a significant reduction in the non-unity of the stretch metric on the corrugated geometry, and this indicates that there's less difference in the relative path length. There is this periodic pattern seen in the stretch on the corrugated model, and this is because using corrugations adds path length in a periodic manner. A similar thing is seen with the felt area metric. The top is the original flat one, bottom is the one with the corrugations. The range in the felt area is much less on the corrugated shell mesh, and this shows that correcting the relative path length through the domain also reduces non-unity in the felt area metric. So this is just looking at the metrics. Now some actual acoustics. So the mesh was the 2D mesh was extruded into 3D to allow the Helmholtz wave equation to be solved. The top plot here is that original 2D geometry, and the bottom one is the one with the corrugations. And this is the pressure distribution at 20 kilohertz. So the domain was excited with a constant velocity over the entrance surface, and then terminated with a rho C boundary condition at the exit surface. And on the original flat geometry, the pressure waves kind of intensify on the outside edges of the bend, and the pressure wavefronts are visibly uneven at the waveguide exit, so it wouldn't be a very good waveguide. In contrast, the corrugated geometry has much more organised wavefronts moving through the domain, and importantly, the pressure waves are more aligned with the exit surface. So that's the pressure at one frequency. The range in SPL was used to look at the acoustic performance of the waveguide over a wide range of frequencies. So this is the maximum range in sound pressure level across all of the nodes on that exit surface. And in this plot I've got the original flat model, a model with the path length equalisation corrugations, and then a model that's also got some thickness adjustments using the felt area metric. So if the range and sound pressure level is 0, it implies the pressure waves are completely aligned with the exit surface of the geometry. So yeah, the range and sound pressure level is significantly lower on the models which have the path length correction. That's the blue and orange line. And then the model which has both the path length correction and the area has been adjusted using that felt area metric performs the best, and that's the dark blue line. Acoustic waves can be controlled through corrugations and thickness variations. These metrics show where the adjustments are required, and the adjusted mesh produces more coherent wavefronts over a wide frequency range. So these metrics can then be used in an iterative optimization loop. The first step is to build a 2D shell geometry, then calculate the metrics on the shell mesh. The stretch metric is used to adjust the corrugation amplitude, and then the felt area metric is used to adjust the thickness of the domain. So that's the basic optimization loop, and it all happens on 2D shell meshes, and the only simulation that needs to be done is the Laplace simulation, which is frequency independent, so it's a really fast core optimization loop. On each iteration, you can also build a 3D geometry, and this lets you simulate the acoustics. So you can look at the correlation between the error shown by the waveguide metrics and the acoustic performance of the waveguide. Example of this is just a simple in-plane bend. On the first iteration, there's been no corrections applied, and both metrics show quite a lot of error. Now moving through to the third iteration, these corrugations have been added, and the error shown in the colour has massively reduced. I've also included the mean squared error reference to the first iteration, and you can see this has come down dramatically. Now moving on to the fifth iteration, again, the differences in the geometry are much more subtle now, but the mean squared error has further reduced. So this is the pressure at 10 kilohertz in the first iteration. The pressure waves are kind of reflecting off that outside edge of the bend, and then there's some modal behavior going on at the exit. And this is the pressure at 10 kilohertz on the fifth iteration. So now the pressure waves are much more aligned with the geometry, and importantly with the exit surface. Again, I've used the range in sound pressure level to look at the acoustic performance over loads of frequencies. On the first iteration, with no corrections, there's a massive range in the sound pressure level. And then as the optimization process moves through, the range in the sound pressure level reduces. So there's this nice correlation between the wave, how coherent the waves are at the end of the waveguide, and then the error shown by these waveguide metrics. So now I'm going to look at a real world device which has been designed using these optimization processes. This is an FEA mesh of the air. The compression driver would go on the back here, and then this here is the cylindrical surface where the sound is radiated from. So each part, the wave shaper bit at the beginning and then the horn section afterwards, were designed using the optimization process, which I just spoke about. I think they were designed separately, and we used 8 iterations of the optimization process. So the first wave shaper section tries to convert circular plane waves into rectangular plane waves. And then the horn section uses lots of separate channels so that you can use this path length correction technique to convert rectangular waves into cylindrical waves. So that's an FEA simulation of the pressure at 10 kilohertz in this design. Just a quarter of it is shown because it's symmetrical in 2 planes, so it saves time on simulation. And it quite nicely illustrates how you start off with circular plane waves at the throat, then rectangular plane waves at the exit of the wave shaper, and then cylindrical waves at the exit, which have nice directivity characteristics. This is what would actually be manufactured. Well, it's a sliced CAD geometry, so it's, I guess, half of what would be manufactured. But it shows the inside shape of that wave shaper, so you've got those corrugations, and it also highlights how the horn has been split up into these separate channels using sort of corrugated fins. Some results. This slide compares 3 different horn and wave shaper configurations. So the first is a conventional wave shaper with an exponential horn. On the left is the pressure at 10K. In the middle is the SPL distribution looking down from the top. And on the right is the horizontal directivity map. So typical of an exponential horn, the directivity gradually gets narrower as frequency increases. Next is a conventional wave shaper with a diffraction horn. So now the directivity is wider up to a high frequency. And this sort of device is really similar to what you'd see in a lot of commercial line array boxes because of this wide directivity. This is the optimized wave shaper with the optimized horn. So now the pressure waves have been controlled inside of the horn mouth to help with the directivity. And there's really wide directivity, I think in this example up to around 13 kilohertz. So that high frequency limit is controlled by how thick you make the channels. If the channel, as the frequency increases, when the wavelength becomes similar to the thickness of the channels, you find that some of the pressure waves actually reflect off the corrugations, But if you want to push that high frequency limit up, you can just make the channels thinner. But then it gets harder to manufacture. So looking at the throat impedance for those same 3 different models I had in the last slide. This is the conventional wave shaper with an exponential horn. So there are some ripples in the throat impedance here, and this is due to an area expansion mismatch between the wave shaper part and the horn. This is a conventional wave shaper with a diffraction horn. So now there's these huge ripples in the throat impedance, and this is due to this large change in area expansion at the end of the wave shaper. And then finally is the optimized wave shaper and the optimized horn. There are a few ripples in the throat impedance, but they're much less significant, and this is due to how the area expansion is controlled inside of the wave shaper and inside of the horn using these separate channels. So some of the ripples which are seen here at lower frequencies in the optimizer model are due to how, as that material which you've used to divide up the horn into separate channels disappears, the horn actually expands faster than if it was in just a conical horn. So that introduces some ripples. And then at really high frequencies, again, it's due to that problem where the sound waves can start to sort of bounce off the surfaces of the corrugations. So to validate the technology, we did some physical measurements. So this is a 150-degree cylindrical wave source. This is really similar to the one on the last slide, except it's a bit smaller. And we created a big measurement waveguide which supports cylindrical wave radiation. So this is the same acoustic load that it would get if it was in an infinite line source. At the moment, the microphone is in the on-axis position, but you can see there's these sort of plugs where you can put the microphone in to measure the horizontal directivity. So this top plot here is the normalized directivity measurement, and the bottom plot is the normalized directivity simulation. I've used 1 dB levels, so you can see the sort of fine details. I think in Pro, people usually use 6 dB levels, so you wouldn't see any of this. But yeah, it's got really wide directivity up to high frequencies, and there's a relatively good match between the measurement and the simulation. So I've just got 2 slides now on just the wave shaper part. So the wave shaper controls the vertical pressure distribution. So this is really important if you're trying to make a good line source. This here shows the pressure at 10 kilohertz on a conventional wave shaper. And the pressure waves aren't quite aligned with that exit surface. So it wouldn't actually create a perfect line source. In contrast, this is the pressure distribution, again at 10 kilohertz, but now on an optimized wave shaper. And the pressure waves are really aligned to that exit surface. This is the range and sound pressure level across a broad frequency range. This is the range and sound pressure level across all of the nodes on the exit surface. And it shows how in the optimized wave shaper, the range and sound pressure level is dramatically decreased. And this is really important because a line array requires coherent pressure waves from each source. So I've got an animation here of the SPL at the horn exit. The one on the left is an example wave shaper with a diffraction horn, and the one on the right is an optimized wave shaper with the optimized horn. And it's moving up in frequency. And you can see how in the example one, there's quite a lot of modal behavior going on, even at quite low frequencies. I think the optimized one works up to around sort of 17 kilohertz. Yeah, the optimized design produces more coherent cylindrical wave fronts to a higher frequency, and cylindrical waves have better propagation characteristics. So I'll look at some other examples of how this technology can be used now, but just to summarize, Lensguide is a really flexible technology. It's applicable to loads of contrasting design problems. Here's some more kind of interesting ways in which it can be used, which are in the patent. It allows both the frequency response and the directivity to be optimized at the same time. And the performance can be tailored to suit specific applications. And there's loads and loads of different designs which are possible. So some examples. The first is a 120 by 60 degree single source horn. So this is a constant directivity horn for a single large compression driver. These are some results which are calculated over the exit surface of this FEA mesh. The top one is the vertical directivity map. The bottom one is the horizontal directivity map. Because they just look over the exit surface of that FEA mesh and don't model any diffraction outside of that, they're very boring to look at. But what they do show is that there's consistently wide directivity. This here is the average SPL over the exit surface, so it's a function of the throat impedance, and it shows that there's smooth response with a low cutoff frequency. There's a 120 by 60 degree toroidal line array source. So this combines 4 drivers to make a single source. This is one that we actually built as a listening demo for the Celestion 100-year anniversary open day. In the middle is a photo, and on the right is the sliced CAD geometry. And you can see how there's these 4 compression drivers which are attached to these wave shapers and then into this large source. So it has good directivity control and a smooth frequency response. These are some FEA simulated results. And it's capable of really high SPL because you have lots of compression drivers which all produce coherent wavefronts even at really high frequencies. We've got a 120 by 120 degree source. I don't think anyone would even attempt that with normal horn design techniques, but it was just a bit of fun. So it's a really compact design, super wide directivity in both directions. I tried to make it quite compact. Perhaps you could use it for ceiling speakers or something like that. And then lastly, a more sort of exciting way in which the technology can be used are 2-dimensional arrays. So sources can be arrayed in 2 dimensions. This technique can be used to make large planar, curved, or even convex wavefronts because the sources are coherent even at high frequencies. These are some results from this FEA mesh. The middle plot is the axial range and sound pressure level. So this is how much the SPL changes moving up and down vertically. Top one is the directivity, and then the bottom one is the average SPL across the exit surface. Yeah, the sources are coherent even at high frequencies, and this is capable of extremely high SPL because you have lots of drivers and each one is only firing into a little angle. So yeah, thank you for listening. I don't know if I went a bit quick there or I've rushed through it or not, but yeah, has anyone got any questions? I can go back through any of the slides.